Okay, hi, assalamualaikum everyone. So my name is HAKIEM. So for today I will talk about theory of resonance state in parallel RLC circuit. So today we have one circuit which we have resistor, capacitor and inductor connect in parallel. Okay, so in the circuit we also applied some AC voltage with a variable frequency. So now we can see that I, IR and IL and also AC are flowing through this resistor and inductor and also capacitor. And let's assume that XL is the reactance of this conductor and XC is reactance of that capacitor. So now whether the circuit is series RLC or parallel RLC, the resonance condition remains the same. That means when XL is equal to XC, then circuit will be in the resonance condition. And during the resonance, if you see the impedance of the circuit will be purely resistive.
Okay, so today I will draw a circuit of RLC parallel circuit at resonance state. So this is the value that we use in this circuit. So the first one is supply voltage in AC. We use 100 volt. So and then the next one is resistor. The value of the resistor is 60 ohm. And next one is inductance. We're using 200 millihenry. And the last one is inductance. This is capacitance. The inductance we use 200 millihenry, and the value of capacitance is 120 microfarad. Okay. At resonance state, there are 4 conditions that apply in the circuit. So the first one is the impedance of impedance of inductance is equal to impedance of capacitance. So the second one is the voltage and current are in phase. The third one is impedance is maximum, and the last one is current is minimum. So in this parallel, the circuit is become like this. So when resonance is applied to the circuit, the inductance and capacitance acts as open circuit. So the total current will be in phase with supply voltage, which is the current become minimum while the impedance become maximum. Okay, that's all.
Hello and Assalamualaikum. My name is Aisyah binti Saiful Bahari. I am from 2BEY 1/2. So in this video, I will show the calculation for our circuit. So this is how our circuit looks like. Firstly, resonant frequency is defined as the natural frequency of a system where it oscillates at the greatest amplitude. A system is said to be in resonance when an external force applied shares the same frequency as its natural frequency. So, the formula for resonant frequency is 1 divided by 2 pi multiplied by square root inductor and capacitor. So, we substitute the value from our circuit and we will get the 32.49 Hz for the answer. Next, inductive reactant at resonance is the resistance of an inductive circuit. An inductor competes against the current in a coil which alters the direction and instantaneous magnetic. This position is comparable to resistance but always possesses a phase shift between voltage and current and dissipates zero power. So, the formula for inductive reactant at resonance, XL, is 2 pi multiplied with frequency and inductor's value from the circuit. Then, substitute the value and we will get 62.83 ohm for the answer. Next, the quality factor. The quality factor of a parallel resonance circuit is the ratio of the energy stored in the oscillating resonator to the energy dissipated per cycle. So, the formula for quality factor is resistance value divided by the value of inductive reactant at resonance, and we will get 0.95 as the answer. Next, bandwidth. The formula for bandwidth is resonant frequency divided by quality factor. So, the answer we will get is 34.2 Hz. That's all from me. Next, IZZUL FITRI will continue the rest of the calculation.
I'm IZZUL FITRI from DEEY 1/2. So I would like to present how to calculate of RLC circuit in resonance state. Okay, for this part, I would like to show you how to calculate the upper and lower frequency point. The first one is FL. So we can use that of the formula FR minus 1/2BW. That we get FR equal to 32.49 minus 1/2 multiplied by 34.2. So we can get that 15.39 Hz. So this is for FL. So the next one is FH equal to FR plus 1/2 BW. So 32.49 plus 1/2 multiplied by 34.2. So we get that 49.59 Hz. For the next part is we can calculate the circuit current at resonance that we call IT. So the IT formula is IT equal to IR. So we can get IR equal to V/R. So in formula we get that 120/60. So we can get that 2 ampere. Or we can assume that we can get with same formula of IL equal to V/XL. So 120/62.83. Oops. So we can get that same with 2 ampere. The next one is current magnification, or we call that Imax. So formula of Imax equal to Q multiplied with I. So we can get that
0.95 multiplied by 2 equal 1.9 ampere. Or same with IL, we can get that V over XL, 120 over 62.83. We get that 1.9 ampere. The last one is impedance, or we call that Z. So Z equal to 1 over square root of 1 over R square plus 1 over XL minus XC square. Oh, we can assume that 1 over square root 1 over 60 square plus 1 over 62.83 minus 26.52 square equal with 31.06 ohm.
Hello, my name is Adam AZROL Beramli and I am from BEY 1/2. Okay, now is the summary for the resonance circuit RLC. The first summary is SL and SC have opposing effects in a RLC circuit. So in a series RLC circuit, the larger reactance determines the net reactance of the circuit. When at series resonance, the inductive and capacitive reactance are equal. The impedance of a series RLC circuit is purely resistive at resonance. And in a series RLC circuit, the current is maximum at resonance. Summary number 2. The reactive voltage VL and VC cancel at resonance in a series RLC circuit because they are equal in magnitude and 180 degree out of phase. And in a parallel RLC circuit, the smaller reactance determines the net reactance of the circuit. And in a parallel resonance circuit, the impedance is maximum at the resonant frequency. A parallel resonance circuit is commonly called a tank circuit. Okay, summary number 3. The impedance of a parallel RLC circuit is maximum at resonance. Current is minimum and ideally equal to 0 at resonance. The phase angle is 0 at resonance. The bandwidth of a parallel resonance circuit is the range of frequencies for which the impedance is greater. Summary number 4. The currents in a parallel L and C branches are equal in magnitude and 100 degree out of phase with each other, and thus they cancel at resonance. The critical frequencies are the frequencies above and below resonance. A higher Q produces a narrower bandwidth. Okay, that's all for summary for this topic. That's all from me. Thank you.